That is to say, relative motion must always exist between the armature and the field in order to generate an EMF in the armature. We can construct an AC motor by closing the loop ends of the armature, thereby inducing a larger current in the loop and creating stronger magnetic fields around the conductors. This is a simple induction motor. The interaction between the conductor fields due to relative motion and the rotating magnetic field causes the rotor to move, but at a slower pace than the rotating field. If the speed of the rotor and the field were the same, there would be no induced EMF. No lines of force would be cut and no field built around the conductor. Obviously, there can be no motor action under those conditions. This, however, is an impossible situation, for if the rotor stops while the field continues to turn, relative motion will have been re-established. Lines of force are being cut once more. An EMF is generated and the resultant magnetic field will cause the rotor to move again. So far, we have rotated the field by physical means, which is impractical. It is necessary to find a way to rotate the field electrically. We saw earlier how 3 voltages 120 degrees out of phase were generated. This voltage can be used to rotate the field electrically. Six magnets set in a circular arrangement represent the field of a 3-phase induction motor. These 3 pairs of conductors, 1 pair for each AC phase, supply the field. Because of the time difference in the 3 phases, the poles will be energized in successive order, thus rotating the field electrically. Since the rotating field is cutting the rotor, it will rotate in the same direction as the rotating field, but at a slightly slower speed. Three-phase motors have special value in situations where it is important to maintain constant speeds under changing loads. Another type of AC motor is the 2-phase induction motor, used especially where it is necessary to change direction of rotation quickly, such as in a radar antenna. The current used in this motor is 2-phase AC. That is to say, 2 separate AC voltages 90 degrees out of phase. Just as in 3-phase motors, the phase difference is used here to energize the field poles progressively, thus causing electrical rotation of the magnetic field. As in all induction motors, electrical rotation of the magnetic field is a primary objective. Again, the rotor turns in the same direction as the magnetic field, but at a slightly slower speed. The 2-phase motor in this installation is called on to change its direction rapidly. This rapid change of direction is accomplished simply by reversing the polarity of only one set of poles in the motor. The polarity of the second set of poles will remain unreversed. The field will now rotate in the opposite direction, with the rotor following at a slightly slower speed. The most common type of current available in most sections of the country is single-phase AC. For that reason, single-phase induction motors are widely used for many and varied purposes. In the single-phase induction motor pictured here, the single AC output energizes both sets of poles simultaneously. There is no phase difference in this arrangement, and so the field will not rotate. As the cycle of the AC wave changes, the poles pulsate alternately. But since there is no relative motion, the rotor will not turn. The major problem is getting it started. If the rotor is started by hand, relative motion is created and the motor will continue to run. But this is not a very practical method. There are several ways to start a single-phase induction motor. One method is the use of shaded poles in the field. A shaded pole is attained by placing a copper ring in a slot over half the pole. The copper ring on the shaded half of the pole increases the inductance of that half. That causes the magnetic field of the shaded half of the pole face to lag behind that of the unshaded portion, creating a rotational effect. Lines of force will emerge from this unshaded section of the pole face first. The inductance caused by the ring makes the shaded portion of the pole lag behind. This alternating pulsating action creates a phase difference within the pole. Let us see now how the use of shaded poles actually produce a torque or turning force in a single-phase induction motor. The single-phase AC energizes the unshaded portions of the poles first and creates magnetic fields in these areas. The phase difference caused by the higher inductance of the shaded sections is responsible for the lag in the development of magnetic fields in them. As the current cycle changes, the same action will take place in all the poles. Relative motion, the basic requirement of an induction motor, has been satisfied. The rotor turns. Because of the relatively small phase difference developed by this method, shaded pole motors start slowly and are not used where a great deal of starting torque is required. There is another way to start the single-phase induction motor. In addition to the main poles, starting poles with separate windings are used. Phase difference is created by using high-resistance wires for the starting poles and low-resistance wires for the main poles. To understand the operation of the starter winding, it is necessary to bear in mind something of the character of the AC power supply. In any pure inductance, current lags behind voltage by 90 degrees. But since the heavy winding is not a pure inductance, but a large inductance, the current will lag the voltage in this winding by less than 90 degrees, say 80 degrees. The greater resistance of the starter winding, because of its smaller diameter, causes the current to lag the voltage by much less than 90 degrees, say 30 degrees. The net effect is then that the greater resistance of the starter windings causes the phase shift to be less than that of the main winding. We now have in effect a two-phase current. The phase difference causes the starter windings to be energized before the main windings. Magnetic fields are formed progressively. This is called a split-phase motor. The magnetic field now rotates electrically. The basic requirement of relative motion has been satisfied, and the motor has been started. When the rotor has attained approximately 25% of its rated speed, a centrifugal switch opens and disconnects the starter windings. The phase shift accomplished by the addition of starter windings is not very great. The starting torque in this split-phase arrangement, although better than that in the shaded pole motor, is still not too good. A third method for starting single-phase induction motors is the use of starter windings with high-capacity electrolytic capacitors. We saw in our last example how a phase difference was developed by the use of starter windings. Now, when a capacitor is added in series with a starter winding, it offsets the inductance, causing an even greater phase shift between the two currents. This is a capacitor start motor with a centrifugal switch. When the motor has attained 25% of its running speed, the centrifugal switch disconnects the starter windings. The centrifugal switch is mounted on the rotor shaft and is the type used on most split-phase motors. Since the greatest phase shift and relative motion is caused by the capacitor start method, it is used in situations where good starting torque is an important consideration. Among the principal types of AC motors in use, the synchronous motor is used in situations where constant running speed is the governing factor. You'll remember that the operation of the induction motor depended on relative motion, that is, the difference in speed between the rotor and the rotating magnetic field. This relative motion induced an EMF in the rotor. In the synchronous motor, however, a different situation exists. Here, a multi-phase source of AC is applied to the stator windings, producing a rotating field, and a separate DC voltage is applied to the rotor windings, producing an independent magnetic field. There is no need for relative motion here. The synchronous motor is so designed that the rotor and the field rotate at the same speed. This is of importance when synchronous motors are used to drive equipment requiring this characteristic. Now to summarize, all rotating generators produce AC internally. The AC character of the output is maintained in the AC generator by the use of slip rings as load connectors. The frequency of the AC generator can be changed by introducing additional magnetic fields. The formula for frequency can be expressed as follows. F, or frequency in cycles per second, equals P, the number of poles, times N, revolutions per minute, over 120. The simplest AC generator shows
the three factors that determine the type of work a motor can produce are speed, torque, and horsepower. Speed is defined as how fast the motor performs its work. For example, a shaft can rotate slowly or quickly. The typical units of measurement for rotational motor speed are revolutions per minute, or RPM. Work is defined as a force applied over a distance. In the case of flywheels, winches, and motors, the work is called torque. Torque is a special type of work that produces rotation. Torque occurs when a force acts on a radius. Typical units of measurement for torque are pound-foot. The torque illustrated here is equal to 1 pound-foot. Horsepower is defined as the rate at which work is accomplished. Years ago, before motors were invented, most work was accomplished manually. It was estimated that 1 horse could accomplish approximately 33,000 pound-foot of work per minute, and thus the term horsepower was born. In modern terms, horsepower is simply another unit of measurement for power and can be translated into watts, BTUs, joules, or any unit of power. Units that measure motor power are typically in horsepower or watts. You can manipulate the connection among speed, torque, and horsepower by understanding how